Okay, everyone, you are now in week 9, the last week of the course. And so this week, what I wanted to give you was just a quick rundown, since it's been 2 weeks since we've had our lecture, about what the expectations are for this last short week, plus a very quick overview of what Chapter 16 was. So we start today on Thursday. By midnight on Sunday night, absolutely, all homework must be turned in. I cannot accept anything at 12:01 a.m. on Monday. Okay, so if there's any questions at all about that, please contact me before we get to Sunday night. So again, repeat, I cannot accept any assignments after midnight on Sunday night. The term is over after that point, so have all your work in. Anything not turned in will be an automatic 0. Okay, so here's what Module 9 has in store for you. First off, we got our standard overview and objectives. Here's your learning objectives for the week. This is all about hurricanes. Remember, I lectured on hurricanes during week 7. Okay, your reading is chapter 16 of your book. If you haven't taken a look at that yet, it's a fairly short chapter. You should have an easy time getting through it. I've posted the chapter 16 lecture slides already, and in a few moments I'm going to give you a very brief rundown of the high points of that lecture. Okay, so we go forward, blog entries. This last week, in those last couple of days, it's your final entry. This is a reflective entry, individually done, talking about your experience with WEAX 201. And don't need it very long. There's not specifying any particular length or content. It's entirely up to you. So it's pretty much, if you write an entry this week, you're going to get your points. If you don't write an entry, you're probably not going to get any points at all. But it's a reflective entry. So think about, what did this course mean to you in both your current curriculum that you're working on with your degree, maybe your job, or even your life. Okay, there's a short video, 3.5 minutes long, on hurricanes and tornadoes. And then right off the go, you got your module assessment. Only 10 questions because you only have one chapter this week. You have 90 minutes to do it. So the two tasks this week are the assessment and your reflective blog entry. Pretty simple. So let me do a quick review of the chapter 16 lecture. Here we go, hurricanes. So the lesson overview is, we wanted you to take a look at the life cycle of hurricanes from its initial easterly wave off the west coast of Africa all the way through the storm becoming extratropical, which means that it's at a far enough north latitude that it no longer sustains its tropical storm properties. We're going to look at the conditions that allow a hurricane to grow and sustain its power, the difference between a hurricane and a mid-latitude storm. I won't touch on that too much in this review, but you will need to know that by the time you take your assessment. I'm also not going to talk about, in this very short review, the difficulty of forecasting movements of hurricanes, but that has to do with how meteorologists use computer models to figure out the movement and the timing of hurricanes. There's a nice little section in your textbook about that. And finally, the major destructive components of a hurricane, and we're specifically going to talk about the storm surge and the flooding, and maybe the tornadoes that are spawned off the feeder bands, the spirals that come off the storm. This was your learning outcome, to relate observed weather to the global synoptic and mesoscale patterns. So if we remember, what we're going to be talking about essentially is this band going across the equator, where between 30 north and 30 south, we have a whole line of convergence. Not necessarily the intertropical convergence zone, but it's at those tropical latitudes in there that are the prime area, whereas we have convergence at the surface to get air to rise. Remember, convergence is one of the 4 ways to get air parcels to rise into the air. And we analyze convergence on a tropical map by using streamline analysis, where the wind arrows come together. That means that the winds at the surface come together, they pile up, and the only place they can go is in upward vertical motion. So off the west coast of Africa, where the waters are nice and warm and the conditions are just right, areas of low pressure start to form, and they move from the east to the west. So they call that an easterly wave of low pressure, comes off the West Africa coastline. And in this particular place, the conditions are just right to start the development of a cluster of thunderstorms and a very small circulation. Eventually, those tropical waves coming off the west coast of Africa develop into, in this case, a hurricane. Now, the anatomy of the hurricane starts off in the center with the eye. The eye is the most clearest part of the storm. It's circular in nature. Not necessarily cloud free, but there's definitely a lot less cloud than the other parts of the storm. We have the eye wall, which is an area of significant wind speeds, a lot of upward vertical motions, significant turbulence for aviation purposes. We have the air rotating in a counterclockwise direction. So that's the cyclonic direction, rotating around the storm. Over the top of the storm at about 30,000 feet, maybe 300 millibars or 250 millibars, I have divergence, okay? What does that mean? That means there's high pressure over the top of the storm that's drawing air out of the center of the storm, kind of like air going over the top of a chimney. Then I have these areas of rain-free areas and spiral bands of rain. They kind of spin out from the storm as if you maybe had a garden hose and were spinning it around, how that stream just kind of waves itself around in the yard. If I took a cross section of that entire section of the storm, we'd see a cyclonically turning area in the eye wall itself, going around that virtually cloud-free eye. As you can see, I have a cross section of upward and downward vertical motions. Wherever I have upward vertical motion, I have significant deep convection, cloud cover, or cloud development. Wherever I have downward vertical motions, the cloud development is highly suppressed. Okay, I have air at the surface that's flowing into the storm, feeding the storm, and I have air flowing in anticyclonic direction over the top of the storm, drawing the air out. It's the outflow, it's the top of the chimney for this. Now there is so much moisture inside of this hurricane that there's a ton of latent heat that's being released. It's almost its own self-sustaining heat engine. That's how much latent heat is released on a storm of this magnitude. And if I looked at it in a cross section using a satellite, I can see exactly where those areas of upward vertical motion are. That's where I'm going to end up with my strongest areas of rainfall. And as you can see here, the red areas on this cross section are almost 50 millimeters per hour is the rainfall coming out of those. Now, what makes the conditions right for hurricane development? First off, you have to be in tropical waters with some very, very light winds. Otherwise, the shear tears the storm apart. Ideally, the water temperature should be greater than or equal to 26.5 degrees Celsius. And typically, climatologically speaking, June to November is the ideal months for that to happen, although hurricanes have been observed in the Northern Hemisphere all 12 months of the year. We need some sort of surface convergence to trigger the development. That's that tropical wave off the west coast of Africa I was talking about. And likewise, I want to have very, very little Coriolis effect, again, to make sure that I don't shear the storm apart. 5 degrees to 20 degrees of latitude is just about enough Coriolis effect to keep that storm sustaining. Okay, the developing storm is just simply a series of clustered thunderstorms around some sort of low pressure system. Kind of unorganized. There's no eye wall per se. It's just a cluster of storms, and you can identify a center of low pressure. And all that convection is releasing a lot of latent heat. That latent heat is feeding those thunderstorms. And then if I can just put some high pressure aloft, I can get some divergence aloft. It's going to continue to enhance the upward vertical motion that's associated with the surface convergence. Again, looking at that same cross-section type of diagram that we had earlier, notice the trends in surface air pressure. Surface air pressure decreases rapidly as I get to the eye wall, and then as I go back out of the eye wall across the storm, the pressure increases, so that at the eye wall, at the eye, that's your lowest pressure. Likewise, your surface wind speeds increase significantly as you approach the eye wall and then drop off drastically once you're inside the eye. The storm is going to die out if it hits either cold water or land. Cold water is going to cut off the fuel of the warm water below it. When it hits land, it's going to hit a lot of friction and slow it down, and eventually the storm just kind of gets unorganized and turns into some sort of mid-latitude or mid-latitude storm. The developmental stages of the hurricane start off with a tropical disturbance. Okay, that's that wave that comes off the west coast of Africa. As it continues to develop and wind speeds increase 22 to 34 knots, we were going to call that a tropical depression. If the area of low pressure continues to deepen and the wind speeds continue to strengthen from 35 to 64 knots, we're going to call it a tropical storm. Finally, as the development gets all wound up and it gets spinning greater than 65 knots, or especially if it's got an eye that's noticeable from satellite, we're going to call it a hurricane. Now, here's the comparison of mid-latitude cyclones compared to a hurricane. This is table 1 in chapter 16 of your book. So take a look at this, and you might want to put a little flag in your book for this in case you're ever asked how to compare and contrast the difference between those two types of storms. Now, in terms of the devastation caused by hurricanes, we've got wind, storm surge, and flooding. Okay, so the highest wind speeds that are going to be recorded are going to be in the east side of the storm relative to its forward motion. Okay, so that's where you're going to get your wind damage. You're going to get the ocean waves are going to swell. We're going to get storm surge on the north side of the storm as it pushes water up against the coastline. Along that coast, we're going to get flooding, okay, as broad areas of water get pushed up on the coast. And additionally, the rivers will begin to flood as well, as either you're pushing water into the river mouth or you have areas of thunderstorms that are lining up parallel to the river and just pouring water into it. Now, sometimes on those spiral bands that come off the hurricane, you can get small tornadoes to develop off them as well. Tornadoes are measured on what we call the Saffir-Simpson scale, where 1 is the weakest type of hurricane and 5 is the strongest type of hurricane. Now, as we mentioned earlier, on the east side of the storm is where you're going to find your strongest winds. Now, if the storm has forward motion, so for example, in this one here where it's got a forward motion of 25 knots, my strongest winds are going to be in the front right quadrant relative to its direction of motion. I'm not only getting the speed of the storm as it's rotating, I'm also adding to it the forward speed of the entire complex. Likewise, the weakest winds are going to be in the back left quadrant. Notice this is much like what we talked about during the tornado chapter. The Saffir-Simpson scale is listed here. This is table 16.2 from your book. This goes through and gives you an idea of what the wind speeds are, plus kind of what the damage should be expected with each one of the category 1 through 5 of hurricanes are. There is a detailed pages of information about some notable storms, and I'm not going to go through each one of these now, but it's very interesting to take a look at what kind of hurricane devastation we've had in our history. Okay, so in a few short minutes, those are some of the highlights of what we had in chapter 16 lecture, hopefully to start jogging some memories of what the lecture was during module 7. Again, the lesson overview, what we want you to get out of this was the life cycle of the hurricane from its initial easterly wave through its tropical disturbance, tropical storm, all the way through its hurricane stages, and then how does it dissipate when it hits cold water or land? Okay. What is it going to take to grow the hurricane? Remember, we got to have nice warm water. The wind speeds have to be just right. You have to have the right type of divergence aloft. All of this has to line up just right for that hurricane to development. There's a chart in your book that shows the difference between hurricanes and mid-latitude storms. Take a look at that. Put a post-it note on that page in case you ever need to reference it. So there's some challenges with forecasting the movements of a hurricane. I'm going to leave that to you to read on your own this week, as well as where are the most destructive parts of that storm, and what are some of those those items that cause the most destruction. Things like storm surge, high winds, tornadoes, flooding, river flooding. All of those come together to talk about the significant devastation that can come from a hurricane. Okay. So with that, that's your quick 15-minute lesson to just again to refresh yourself of what we did 2 weeks ago during our last lecture. My, how time flies. Okay, as a reminder, don't forget to do your class evaluations. Those are going to be due in just shortly after the course is over with. So please fill out those course evaluations. Those are significant for me as well as for Embry-Riddle as we continue to improve the course. Thanks again for all you guys do out there. Continue to be safe. Thanks for serving your country. Thanks for being great students with Embry-Riddle, and I look forward to seeing you out there in the industry.